Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in lecture 12. Student, basically we covered in lecture number 11 we covered the design of analysis and design of column. Okay, and you see how we design that column, and now we have to design footing. Okay, so to design a footing, we must basically understand the basics of footing. Okay, so let me show you some videos regarding a column. Okay, here you see that there is you see we have a column. These are the column main bars or longitudinal bars, and they are the hooks are provided. Okay, you see here, and similarly you see the how they basically bind the bars. Okay, and you see this is the top reinforcement and the lower one is the bottom reinforcement, and okay, these are the top reinforcement and how they are providing basically the bars. Okay, so this is the way how basically columns are, this is the whole detailing clear. And okay, these are the bottom bars and these are the top bars in bottom layer. Okay, that is the on the bottom surface of the footing mat. Okay, this is the column reinforcement. You see the hook is provided for better anchorage of the bars. And you see the length of the bar is will be how much, it is basically provided that the next for the ground story bar should be lapped with this bar. Do not we are providing the full length of the bar. Okay, and here you see the remember this hook have no role in in anchorage. Remember, this is although it is practice, but in compression basically this hook have no role, and I have recorded a lecture on it. Okay, this is called splice in compression basically, but this have a no role. Remember. Okay. Let us you see the bar length. Remember, uh, this is from the surface of the ground. It is left the the bar should extend for a distance of LD, or you can say for a lap length. Okay, and let me show you. Okay, that I will discuss it in later. Okay, and let us see this video. So first of all, PCC is laid down. Then remember, cover blocks are placed. This is 3.5 or 3 inches cover blocks, and then bars are placed over this cover block. Okay, and this is first layer, bottom layer, this is the top layer. Okay, bars in direction 2. Okay, and hooks basically 12 dB. Then remember the bars of the column is provided. Okay, and they are left in this shape. Okay, and remember, here I want to show you that if let's say my ground level is here, so I have to keep this distance such that the top story bar should be laid properly with the column bars. Remember. Okay, so remember the depth of your foundation plus the lap length. Okay, then shuttering is provided, and finally the concrete work is basically done. Okay, and then it fills up with the concrete. Clear? So this is the way that how a column is constructed with a footing. Okay, and now let's start okay our calculations. Design of footing, we need service load. Okay, and at the beginning of this lecture 1, basic lecture 2, I discussed that why we calculating these service load, because we need this service load in the design of footing. Okay, so that why you see here the slab load, that is service load, we already calculated this in lecture number 2, and the service load you see here, this one. Clear? And the next one is the total panel load. Remember, here we have panels. Okay, remember, for example, if we are designing for this footing, okay, let me change the color for this footing, for this column footing. So all the columns are symmetrical, the beams are symmetrical, so that's why I am using C, because the C panel is the bigger one. Okay, although B and C are closed. So remember, the effective area, you can say the tributary area for this column will be the half of that. Okay, will be the half of this panel, will be the half of this panel, half of this panel, and so on. Clear? So this will be the tributary area for this column. Okay, and that load will finally transfer to the footing. Okay, so therefore I need, and remember these are square columns, square panels, sorry. So that why the distribution of loading basically is same in either in this direction, okay, and either in this direction. Clear? So already we discussed it, okay, in the design of, basically in the design of beams. So these are square panels, that's why the loading will be same in each direction. Clear? And here you see that just multiply the panel area, that is 19 by 19, we got 53 kip. Remember, this 53 kip is nothing, it is the weight of the total weight of this panel C. Okay, now we have to distribute them, okay, in longer direction and shorter direction, but this panel C is a square, so that why we say that equal load will be distributed either in this direction as well as in this direction. Okay, equal loading will be distributed. So 53 divided by 2, basically this is 53 divided by 2, okay, and this one is also 53 divided by 2, okay, this one. But as 53 divided by 2 is in both direction, so we have to count for one direction, that's why we have to further divide this by 2. Remember, we have to further divide this by 2, so that why we got 26 point something. Clear? Because if you divide 53 divided by 2, so it will give you the load transfer in one direction, and you see when the load is in one direction, so they are further distributed the load in this direction as well as in this direction, so that's why we have to further divide 53 divided by 2 by 2. Remember, this is an important point. Okay, so let me show you the rest of the calculation. Here we have here, so half of this load will transfer to each direction. Clear? Now because the panel dimensions are same, that's why W and WB will be same. Okay, 26.5 kV. Okay, see page number 136. Load per foot of beam. Remember, 26.5 is further divided by 2. Now this will give you load distribution in one direction. Okay, but as we have to need to determine the load per linear feet or per strip foot, okay, so that's why we have to divide it by 19, and I will explain this in when we're designing basically the load distribution for beam. Okay, we will explain this, but let me show you here that remember this is 26 point something, it is in each direction. Remember, basically let's I will show here. Okay, and for example half loading will be, this is 26. Okay, this is 26, but this is 26 is the total load of the half panel. Now I have to obtain it by 1 linear feet. Okay, so that why I have to divide this 26 by this transverse span length, that is 19. So that why I have to divide it by 19. Okay, so per linear feet of the beam load will be obtained. Now let's see further, and here we have I'll multiply by 2, because multiply by 2 is therefore because we have 2 panel from this side as well. Okay, from this side as well, so that why it will be further multiplied by 2. Clear? And now we have to we determine basically 1.4 kg per feet. This is the load which is coming from the slab to one beam basically. Now beam reb weights, okay, we have 18-inch beam depth total, but the rib weight depth is 12.5. Remember, 18 minus 5.5. Okay, so we got 12.5. 12 inch is the beam width, so multiply this and divide it by 144 to convert it into square feet. Multiply with density, you got this one. This is the beam rib weight. Clear? And the slab above the rib, we already know this, that this is the service load. Remember, this is per square foot load, which is converted to per feet. Okay, and we already calculated this. Okay, here you see this one. And total service load on beam, now you add this one and this one, you got 1.71. Clear? Load transfer to column from end span. Now this is important. These points are important. Remember, as we see here in this beam load calculation, so here you see, from this is my column, and this is these are basically factored load. Remember, not service load. So from one side, this is the mid span, or you can say central span. Okay, and mid span. Okay, and this is the end span. Remember, this is from end span. So the end span reaction basically at the which is the, as this is the first interior support and this is the exterior face, so here is 15% more reaction. So that is why we are using 1.15 WULN, and here you see this is the 15% more of that reaction. Okay, so this is only the difference. You must keep this in mind. Here I am using 15% more of that one, and the rest of here you see this is WU divided by ln divided by 2, and you got 16.2. Okay, clear? And let me show you. Remember, if I assume this column, okay, let me draw it. This is my column, and I assume this and this beam. So here we have, okay, and again I have this column, okay, and here we have. So this is my end span. So from this end span, the reaction will be 15% more than the reaction which is right here. Okay, and the reaction will be here is WULN divided by 2. Okay, so that's why I'm using 15%. Similarly, for this beam as well, this is my end span and this is my central span. So if I draw the diagram like in this way, okay, this is my beam, this is my column, this is my column, and that is my beam. Okay, so from that side I have 15% more, and from that side I have the same, this one. Clear? And from this side I have this 15% more reaction. 15% means 1.15 times WULN divided by 2. Clear? So you don't need to be confused in this calculation. Okay, one side you have 15% more, other side you have just this 16.2 K, and similarly you have 4 sides, so that's why you have to count for 4 sides calculation. Clear? Now you see total service load on column. Now see 18.7 is 15% more, and that is the normal one. You just find out for 2 sides, and for other 2 sides you just need to multiply it with 2. Okay, the same case is here. See, you just add these 2 okay, this 2 and multiply with 2, because the beam is from that side as well. Okay, So this is a simple calculation. Remember, this is not, you don't need to be confused. From this side, WU ln divided by 2, and from that side this is 1.15 times WU ln divided by 2. So you need to add these two, and from the beam which is coming from that side, okay, you just need to multiply these two values with 2. Okay, so this will give you the total service load. So I think so the calculation is easy, clear? So that's why I gain 670 kF, that is my service load, clear? 70 kF. Now load of column, 16 load of column, yes, 16 feet long column or high column, and 12 by 12 inches its cross section. Remember, 12 inch by 12 inch. Okay, so divided it by 144 to convert it into square feet, and multiply with the density. So this is the weight of the column, and total service load is 70 plus 2.4, that is total service load is 72.4 kF. And now my factor load PU, that is 102.6 plus, this is the column weight, so you have to multiply column weight with 1.4 factor or 1.2. okay, you can use one can use 1.2 or 1.4. okay, and this is 102 is my PU, which is already calculated in the design of a column basically. Okay, let me show you here. This is my PU, clear? So now this is my total concentrated load on the footing. Okay, this one PU, this is my PU, and this one is my total service load, clear? Concentrated service load. Now I have to obtain, I need to find out the footing area. So let the average density of soil, because we need average density, because you see here in this picture, this is my ground level. Okay, this is my ground level, and you see here there is concrete and there is soil. Okay, so soil density is you see here 107 or 110 or 100, sometime 100 pound per, okay, per cubic feet, and that concrete density is 150, clear? So we don't know at this moment, the beginning, at the initial moment, that what will be the depth of this footing. It may be 2 feet, it may be 3 feet, it may be 1 feet. Okay, so we can't say. So therefore we using the average density 150 plus 100 divided by 2. We got average density 125 pound per cubic feet. Clear? So this is the reason behind this density. Okay, this density, why we use this average density. Clear? Effective bearing capacity at 4 feet below, this is my depth level. Okay, 4 feet below. Now QA is already QA is basically given, that is 2000. Remember, 2000 pounds per square feet. So my QE is basically QA minus the load. Okay, that load which is applied by the overburden. Okay, and due to the concrete soil. Okay, so just subtracting, you got 1.5 kg per square feet. Now you need area of footing. So area of footing is nothing, it is just only the service load divided by the QE. Remember, service load 72.4. that's why we calculate service load. We need service load for calculation of footing, and this is my effective. So I got 48.26 square feet. If I'm using a square footing, so just taking square root, we got 6.95, and let's say we're using 7 feet. So my revised area of footing is now 7 by 7, which give me 49 square feet. Okay, this calculation is simple. Factor soil pressure. Okay, so this is 106 is my factor pressure, that is concentrated, total concentrated load, dividing by 49, that is my now the revised area of footing. This give me, this is basically QU. Okay, this is basically QU. Remember, this is QU, 2.163 kg per square feet. Now let's say I'm using my HF, that is my footing depth is 12 inch. I using 1 feet of the total concrete depth. Remember this one. Let me show you this one. Okay, I'm using the concrete depth or the thickness of concrete mat, you can say, this is, let's say HF is equal to 1 feet. Okay, so I need basically, if I am providing bars right here, so I need effective depth, that is D. Clear? So, and remember, in case of footing, we have to provide an effective cover, or you can say, okay, cover is 3.5 inches or 3 inches, not less than 3 inches, remember, because there are more severe condition in footing. So chances of corrosion of steel. Okay, so I'm using 3.5 inch, give me 8.5 inch. Remember, this is my now effective depth. Now I have to calculate punching shear. So punching shear, you all know it, it basically exists at a distance of d by 2 from the face of the column. You all know this well. You see, this is my footing. Okay, this is my column, and punching shear exists basically from the face of the column to fourth side, basically all over the side, d by 2. So then they basically forming, like, let's say this is my footing. Okay, its width is 7 feet. Clear? Its width is 7 feet. So this is the parameter, okay, punching shear parameter, B naught, which is known as B naught, and this is d by 2, this is d by 2, d by 2, and d by 2. So that why the parameter, the one side of this parameter, of this dotted line, which is my punching shear zone area, is 12 plus d, and if I multiply it with 4, I got this B naught. Okay, I need this B naught for calculation of a punching shear. So you understand B naught, what is B naught? And here we have, to calculate the punching shear, I have a formula for punching shear, QU times A minus B plus D divided by 144 square. Okay, 144 is out of the square, remember. So QU is 2.16, already calculated. A is 49 and B is 12 plus 8.5. B is the, basically this is the B of column, side of the column, remember. And 8.5, remember, if it is a rectangular column, if it is a rectangular column, then this formula can't do work. Okay, we have to revise this formula again. Okay, because in that case your B naught will be different. Okay, your calculation in B naught, because here you have H and here you have B, so then the calculation will be different. Remember, this point should be kept in mind. Okay, now you see, we do the calculation. Remember, we have to take square of these two values. Okay, we got our punching shear is 99.54. We already calculated B naught, that is 82 inches, and my punching shear capacity of the concrete is 45 FC prime B naught. It is defined by the ACI code, so 149. So my punching shear capacity is more than my punching shear, so that why the depth of the footing is sufficient for punching shear. Now I have to check it for beam shear as well. So in case of beam shear, we have to multiply QU with the shaded area. Now what is the shaded area coming here? You see, this is the column and this is the critical zone for punching shear at a distance of d. So what will be its width? Okay, what will be its width? So from the center line, basically this distance is distance is 3.5. Clear? And my d is basically how much? My d is basically 8.5 inch. So just 8.5 converting into feet, subtracting this from this, you got your this distance. This is 2 point something. Okay, 2 point. Here I have this one, 2.29. Clear? So that distance is basically 2.29, and multiply with 7. Okay, multiply with 7. So this is basically this shaded area. Okay, you see the shaded area, the width of this shaded area is 2.29. Clear? 2.29 feet, and the width is, the length is 7 feet, and this exists at a distance of d from the face of the support. Clear? And from the face of the column, this length is basically 3 feet. Remember, 3 feet. So 3 feet minus this d. Okay, you just need to convert that d into feet. You got this 2.29. Okay, now this is my VUB, that is my beam shear.
Now the beam shear capacity defined by ACI is 2 pi FC prime under root 2 BD. So you just need to plug the values. You got 76, which is more than 34. So here we are set. So this mean that it clarify that the depth of the column is sufficient for taking that punching shear as well as beam shear. Clear? And now my flexure design. Okay, so for flexure design, basically it says critical section will be at the face of the column. Okay, and here we have QU times L square divided by 2. Okay, remember the critical section, here you see this is my column, this is 1 by 1 column, and this line basically denoting the critical section for the beam, for the movement, critical movement. So there will be the critical movement, and just consider it as a cantilever beam. Okay, you just need to consider as it is a utility, but it is an inverted cantilever beam. The load should be applied from the bottom, remember, and this will be bending like in this direction. Okay, so here is my critical moment. Okay, mu. So mu is nothing, this q, this is the loading, this qu is basically my loading. Okay, and this is my length, that is L, and that L is from the face of the column. You see this is 3 feet. So that why my movement will be how much? Mu loading times L by 2. You all know this better. Okay, so that's why I'm using this formula. I got 116 at kif inch moment. Now I have to design for this movement. So you all know this equation, well-known equation. You need just to plug this movement here. You got your AS, that is 0.26. Now my AS minimum, you know this rho minimum BD. The B is basically here we have the B is 12 inches and D is 8.5 inches. Okay, so just plug the value. Remember, we are just designing for this one strip. Okay, if we are designing for the whole this portion, so then we need to multiply 7 here. Okay, remember sometime we use the whole length. Okay, we use the whole length. Not in that case, we are basically designing for this whole portion, not just only for this 1 feet strip. Okay, so this you must make sure this difference. Okay, and now my AS minimum is greater than AS, so that's why I'm using AS as my provided. Remember, this is now my AS provided because I have to maintain that ductility check, and D is 8.5. Okay, so I need to find out the spacing, so I'm using number 4 at the rate of 7 inch. It will give me AS 0.34, which is equals to 0.34 as minimum, and my D is this one. So if I using this amount of steel and with this in effective depth, whether it will support this movement 116. So to check that, you need to plug these values into the moment design capacity equation. I use this and I explained this okay already. So A is 0.34 and D is 8.5 inch. You do the calculation and you got 151 inch, which is more than mu, so we are okay. Now we have to check the development plan. Remember, this check is very important, and I already explained this in my lectures, which I already given you a reference, okay, available on my channel. Remember, for example, if I'm putting the bars right here, here is my face, so this is my critical face. Okay, so the length is this much. Remember, I have to subtract this 3 inches for side cover. Okay, so remember, this length from the edge of the footing to the face of the column is 3 feet. You can say 36 inch. So 36 minus 3 inch, it will give me 33 inch. Okay, now this 33 inch is basically available to me. Okay, now you all know better that the bar must extend from the critical section. Remember, if you have any critical section, the bar must extend for a distance of LD or development length. For example, if you have a cantilever beam, okay, if you have a cantilever beam, right, in this case, so the bar which you are placed here, as